So before we get going with the seminar, I'd like to introduce our head of school, Peter Sommer, who would just like to say a few words before we kick off with the seminar. Thank you.
The key adjective there was few. So a few words. So I know I have people here who are going to stop me from talking. I am very excited, so I may talk a bit too quickly. Excited to see all of you. Excited especially to see you. And for those of you who are new to the school, and I think there are a few of you here, this is the Cambridge Friends School. We are a Quaker school, pre-kindergarten through grade 8. It is the mission of our school to provide an outstanding education guided by Quaker principles. And in thinking about this evening, it occurred to me that Quakerism came to be at the same time as the scientific revolution. And think about the 17th century. And you think about what made for such a revolution in science. That the scientific method was a new approach. And it was an approach that the experimental method that in theory was accessible to everyone. Now, we may take that as a given, but that may not have been the case all the time. In other words, there wasn't a scientific priesthood that would tell us what truth was and truth always would be. And that led to a revolution in science. Now, saying that, let's think about the same time in the 17th century, about Quakerism. And what we had is now the beginnings in the religious society of France of an experiential religion. One that wasn't mediated by a priesthood, one that dealt with community, and one that believed in continuing revelation. I think there are remarkable parallels. And I think those parallels have something to do with why Quakers, way out of proportion to their numbers, were in the contributions to science over the last few years. Also, to think about the words of George Fox, who was the founder of the Religious Society of France, the founding Quaker, who on a number of occasions in this journal says, "This I know experimentally." And I think those words were chosen very carefully. Think for a moment now of a 17th century visitor coming now to Cambridge in 2013. And if you just imagine what that might be like, it would be incredible. I mean, imagine this, her coming here, and her mind would just be a swirl with everything that's going on around her. Our means of transportation, our means of communication, these things, these computers that we have in our pockets. It would just be radically different. Now imagine that same 17th century visitor walking into a school building. And she'd say, "Now I feel it." And that's a problem. And what the fact is, all this is changing around us. But in all too many schools, even here, that our model of education is all too often someone like me talking to a bunch of people, pouring in information as if there was liquid into some sort of empty vessel. That's been the same for way too many years. What's different here is that we know it has to change. And what we need to think of is how education can change, because we know that we need to liberate students who actually are already liberated. We don't need to do that. We need not to get in their way as these minds are constructing the reality around them. And that's what often, fortunately, we do very well at this stage. Now, is technology the answer? Actually, it's not. It's not the answer because you can look around us and you can see what technology does. It's facilitating that old type of learning that I told you about. We need a new vision of how to do that very differently. And we are working towards creating that vision here at the Cambridge Principal. To help us do so, we look at what's going on in the world around us by some key thinkers who will challenge us, will prod us, will say we need to do things in a new way. And it's just that type of challenge that we look forward to. Key people to help us really shine a light on these new paths are the people here tonight, who I know will prod us and challenge us and tell us ways that we may be thinking about doing things anew. We're very fortunate to have these three individuals with us here tonight. Neil Gershenfeld is the director of MIT Center for Bits and Atoms. That laboratory has just done remarkable work, and both with physical worlds and digital worlds, looking at how to use computers to make creations, anything from thinking about quantum computing to making musical instruments. Their technology that's come out of that lab, one can see in the Museum of Modern Art in New York, can see in villages, Indian villages, can see in the White House, can see, importantly, in community centers around the world. You'll see some of that tonight. Neil has authored many technical publications and a number of books, including When Things Start to Think, The Nature of Mathematical Modeling, The Physics of Information Technology, and those of you who have done any Googling see Neil has been featured in many publications all around. He's a fellow of the American Physical Society, has been named one of Scientific American's 50 leaders in science and technology, and has been selected by Foreign Policy as one of the top 100 intellectuals. I don't know if that's 100 intellectuals in Cambridge or 100 nonetheless, he's in very good company. Neil has a BA in physics from Swarthmore and a PhD in applied physics from Cornell University. And most dear to our hearts, Neil is an alumni parent at the Cambridge Principal. We're lucky to have Sherry Lassiter with us. Sherry's director of the Fab Foundation. And the Fab Foundation has a remarkable mission. And the mission of the Fab Foundation is to provide access to tools and the knowledge and financial means to educate, innovate, and invent using technology and digital fabrication to allow anyone to make almost anything. Prior to her work with the foundation and with the MIT Center for Bits and Atoms, Sherry worked in science journalism as a writer and as a producer for television series, including Scientific American Frontiers, Discover the World of Science, Science Times, and others. And we're thrilled to have her here today. Jan Morrison is president and CEO of the Teaching Institute for Excellence in STEM. Those of you, as acronyms start flying around, STEM is science, technology, engineering, and mathematics education. Jan has served as the senior consultant for college-ready STEM education, as well as post-secondary success for the Bill and Melinda Gates Foundation. You can put in a good word for us. And served as an advisor to the White House and the Department of Education. JAM was counsel to the National Academy of Engineering as it was developing its report and reviewing the next generation science students for the country. JAM has designed and implemented STEM curriculum and instructional programs throughout the country, and has worked to set up schools that can serve as models of STEM education for others and for all of us. And in this case, dear to my heart, a former science teacher, and former school administrator, including time, I was going to say serving time, that's the including, and I will see why, working at many independent schools, including the French School of Art. And with that said, I'll hand things over to you. We're looking forward to more.
Thanks, Peter. It's fun to have an excuse to come back. So we're going to tag team. Tonight's going to be about a digital revolution in fabrication. I'm going to talk about the digital fabrication piece, and then Lass and Jan, who know much more than me about many things, but education, we'll talk about education. So to understand what this is about, computers were analog, phone calls got worse with distance. We now have the internet. Computers were analog. Vannevar Bush made this at MIT. It's a room full of gears and pulleys. It was an analog computer, and the longer you ran it, the worse the answer was. Computers are digital. We're now in the process of digitizing fabrication. So think of this as the third digital revolution. But it's going to be bigger than the other two because it's taking the programmability of the world in the computer and bringing it to the world out here. We're learning how to program reality. This is a meeting I ran recently with the White House where I gathered really all of the relevant agencies plus the leading researchers to look at an emerging science of making things, the science of digital fabrication. Presentations or videos at that site if you want a lot of detail. I'm going to give you a tour, just a little bit about what that looks like. And what came from it is this roadmap from computers controlling machines to machines that can make machines to putting codes into materials and finally programs into materials. So a little bit about what each of those look like. This was 1952, and MIT made the first computer-controlled manufacturing machine. This was an offshoot of Project Sage, and this was the Whirlwind computer, which was essentially the first computer you could use in real time rather than giving it a batch job and waiting for it to come out. And at the time, the Air Force had some complex aircraft parts nobody could figure out how to make by turning cranks on a machine. And so there was an epiphany that you could connect the computer to the machine that was connecting to what seemed like wholly unrelated things, so the computer could turn the cranks on the machines. And so that's when computer-controlled manufacturing started. From there, there's now about 20 different processes by which computers do stuff. And so in a facility like CBA, which I started because I could never tell the difference between hardware and software, physical science and computer science. So I invented it as a place where I fit. We have one of each of these, and so you can cut, burn, spin, extrude. These are all ways computers move machines to either put material down or take material away. And each of these has relative strengths and weaknesses that let you manufacture. So that was up to, that's the current version of what started in 1952. Here's the next step. These are all machines made by my students. So now it's not just rapid prototyping, meaning making a thing quickly, but it's rapid prototyping of rapid prototyping machines. So this is now work on the technology to make machines. And so here, the work behind it is structural systems and motion systems and path planning and things like that. This one dispenses liquids for biology. This one prints. This one makes molds and circuit boards. This one turns. This one slices. Again, all those different processes. But now what's interesting is making the machine becoming as easy as making a project with the machine. And so in particular, these machines can make most of their own parts. So once you have one of these machines, we're beginning to start this viral spread where the machines can then make more machines. And so that's where we are today. Coming off from this, there are a number of commercial projects emerging from the students who worked on that. One is the other mill, and then in the back is the Form 1. This is a print from the Form 1. The machine's in the back. And after the talk, you can go see the machine and prints with it. This was started by former students Max Lebowski, David Craner, Natan Linder. And what they wanted to do is, there are very expensive high-end commercial 3D printers that cost maybe $50,000 and have very expensive materials. Then there's low-end consumer ones that cost a few $1,000s and make terrible parts. They wanted to make a consumer machine that could make beautiful parts at high resolution. And the result was this Form 1 that makes these gorgeous parts. And so after we're done, you can go back and see that. And it's now a few $1,000s, so you could have one in your home. So that's where we are now. Then here's the step that came after that. So that's my son Eli looking embarrassed. And that's his sister, and back when they were at Friends. And we were just beginning to start to deploy the equipment to do digital fabrication. And to help me develop it, I started bringing the machines home so I could work in the middle of the night on processes with the machines. And so one of the machines was one of our favorite ones, a computer-controlled laser that cuts out parts. And so we had a laser cutter at home, and I was doing a project with the kids to show them how to use it, and they thought, boy, the laser's cool, but my project was really dumb. And so they had a better idea, which is to make a construction kit. And we were just using cardboard as the material, and so they had the idea of making a snap-together construction kit. I had to help them get the dimensions right for fitting the parts, but the basic scheme for the parts they designed. And so instead of buying Lego from just a cardboard box with the precision of the laser, you can make as much as you want. And in particular, you can then customize Lego to make a Lego set that does exactly what you want. So that was GIC. It started as Grace's invention kit, because she started, and then Eli joined and it became the Great Invention Kit. And now it's actually become a technical term. People just talk about GIC because we're up to about, I think, 5 graduate theses at MIT based on the work of the, were they 8 in that picture, maybe? No? How old were they? 6. Based on 6-year-old. So yeah, here's the current work, and it's very serious. The transition we're now migrating through is today's machines that either print or cut. The computer's digital, but the material's analog. You're continuously depositing it or removing it. If you think about a child playing with Lego, it's very different. With the Lego, you don't need a ruler to position it. The metrology is in the parts. When you snap the parts together, you can detect and correct errors. So a Lego tower is more accurate than the motor control of the child. You can join dissimilar bricks, and when you're done, you don't put Lego in the trash, you separate the bricks and use them again. Those are exactly the properties that led to digital communication and computation. And in fact, that's not a new thought. That thought dates back 4 billion years. That's the evolutionary age of my favorite protein, the ribosome. That's the protein that makes proteins, that makes the parts of your body. And the molecular Lego are amino acids, but they behave exactly like Lego in the sense. And so the transition we're just now passing through is, instead of continuously adding or removing materials, actually making the materials digital in this discrete way. That may sound abstract, but think about an old analog telephone versus the internet. That's exactly the difference. And so in working on this transition to digital fabrication, what my students had been doing was making complex structures that you could assemble. And in GIC, what Grace and Eli did was show how you can make complex three-dimensional shapes out of a two-dimensional part based on this joint system. And my students hadn't been thinking about making 3D structures from 2D parts, but the 2D parts are much simpler to make. And so this is now a series of GIC pieces, starting from macroscopic down to, that's a human hair, and then this is so microscopic, you couldn't even see it on that slide. On many different length scales, it's the GIC construction system, but making them very large and very small, based on the design scheme dating back to the 6-year-olds. And so, for example, this is now a circuit. When you make electronics today, you have to etch circuits and put parts on it. This is using those GIC parts out of electronic materials to make snap-together circuits. So you can build electronics this way. And not only can you build electronics, but you can also unbuild electronics. Instead of, when you're done with this, putting it in the trash, you can take this apart and use the parts to make something else, just like you do with Lego. This is what the machine looks like. In the back is a 3D printer. Now for these Lego-like parts, you need assemblers, not printers. And so this is work being done by a current student who worked on another 3D printer, the MakerBot you may have heard of. And now he's working on assemblers to place parts for these digital materials. And the goal of that part of the project is to make a tabletop machine much like the one in the back, but that can make integrated circuits and advanced electronics as a tabletop process. Here's another kind of Lego that grew out of that project, which is, this was a recent paper from a student that was in science. He's now at NASA, showing how to make the world's highest performance materials. And here, now, the materials are loops of carbon fiber, and the assemblers are like insects that crawl around in the structure, placing the parts. But instead of having to have like a global gantry to do it, the insects can crawl around in the structure, placing the parts relative to the structure to grow it as you're building it. And that's part of a project to make not only airplanes, we're working on airplane printers, but airplanes that can change shape. So you snap the parts together, and instead of having flaps and controls, you can actually deform the whole structure and make it change shape. And so we're working now with Boeing and Airbus on making literally airplane printers. Instead of billion-dollar supply chains to make the parts, we're making machines to crawl around and grow airplanes. You can't 3D print a plastic airplane, but we're making assemblers to grow them. And let's see. And then the final step in that sequence is we then started developing ways to literally turn codes into data. So this is a project where you take a string of ones and zeros that describe an object, and then the strings actually turn into the object, just like proteins fold. And so the data doesn't just describe the thing, the data literally becomes the thing. And so this is the math to turn data into things. And then we've implemented that in many different versions. One of the versions we did, this is a part of a robot that can change shape. It's a robot that can turn into any other robot. And the fun trivia on that is that project was done by a student, Ara Kanayan. Motorola just announced Project Ara, which are phones you can disassemble and reassemble. And Project Ara is named for Ara. Who did it. He did the engineering, and the marketing people thought it would be cool to name they liked the sound of his name, and so they named the project after Ara. And so what all that adds up to is this very close historical parallel. There were mainframes, then mini computers, then hobbyist computers, then PCs. And that's the path we're recreating. There's starting from 1952, the mainframes of fabrication. Then the fab labs you'll hear a lot about tonight are like the mini computers. They're not yet personal scale, but they're the size of a work group. The machines that make machines are analogous to the hobbyist computers. This was life-changing for people like me. The Altair was something now individuals could own. And when it first came out, the killer app was you would flip switches to load a binary program. You would start it, and the lights would blink. It was life-changing. Literally life-changing for a whole generation because it was the first computer you could own. And then comes the PC. The 3D printer today is not yet the PC. The distinction is in the PC was a processor, a memory system, a non-volatile storage system, a power system, a communication system, a graphic system, all of these separate systems put into one box. So you just turned it on and it worked as a box. The 3D printer today is one of those systems. The research is taking all of those capabilities and merging it into one. That's about a 20-year roadmap to get there. But the lesson to draw from this is this. This is Ken Olsen. MIT created the TX series, which are the first transistorized computers that came from the project Whirlwind. That got commercialized as PDPs from DEC. This is Ken Olsen, who founded DEC, and very famously said nobody needs a computer in the home. DEC is twice over bankrupt. Compaq bought DEC, HP bought Compaq. You have computers in the home. And the point is the computers in the home, not for inventory and payroll, but to talk to friends and listen to music and do all the things you do. And so the lesson to draw from this historical parallel is the internet wasn't invented here, it was invented here. Video games, word processing, email, all of that happened in the mini computer era. We still have 20 years to go in the research, but the equivalent of the historical moment of the invention of the internet is what's happening today. This isn't a story about the future. You're right at the moment analogous to when the internet emerged, and that's this digital fabrication revolution now happening. I first appreciated that when we were doing this research on digital fabrication, but the one question I hadn't asked is who cares, why? Just because it was so interesting, we didn't even think about why. I got all of these machines to do the research, but it would take too long to teach students to use everyone separately. And so I started a class called How to Make Almost Anything. And that wasn't meant to be disruptive. It was just aimed at ARA, aimed at a few students to do research. And every time I teach it, hundreds show up trying to get in. 2 students here have joined from it. Out of it, I can pick a small group out of the hundreds that try to take it. So that was the first surprise. Then the second surprise is why they were there. They weren't there to do theses on digital fabrication research. They wanted to make stuff. And in retrospect, I guess it's not so surprising in a class about making things, people would come to make things. And then the third thing is what they made. So I would cover all of this stuff, and then students would do projects to integrate them. And Kelly was a sculptor. She was a star the first year. She made a device where when you're mad, you can save up a scream and play it back later. This was a web browser that lets parrots surf the internet. This was an alarm clock you wrestle with and prove that you're awake. This was a dress instrumented with sensors and spines that would defend your personal space. And that would happen so consistently that what I finally got was the killer app of digital fabrication is personal fabrication. And the point of personal fabrication isn't to make what you can buy at Walmart. It's to make what you can't buy at Walmart. It's to make products for a market of one person. And the students were showing personal fabrication as the reason for digital fabrication. So then what happened was, you all paid for this, thank you, through the NSF. We got the NSF on a good day where we said we wanted a facility with one of any machine to make anything. And NSF said yes. And so that was about $10 million of stuff. Then a couple years in, Congress passed a rule that agencies needed to show social impact. For the experts, this was GIPRA. And so GIPRA was passed, and NSF had to show Congress to measure social impact. And so having no clue how to do it, NSF turned to the grantees and said, measure social impact. NSF didn't know how to do it, but they asked grantees how to do it. We didn't have a clue, but we did know the machines were much more interesting than talking about them. So we had this idea that it's a 20-year roadmap, but what if we took the mini computer equivalent, not $10 million, but about $100,000 in roughly $10,000 machines, and made a community lab that was analogous to the stage of the internet and set it up in a community center. And so the very first one we did was with Mel King at South End Technology Center, who has many CFS connections, and it's still there at SETC in Back Bay. And then they spread, and Sherry will tell you about that. This is one of our favorite labs. It's in Vestmannaeyjar, Iceland. If you've ever seen a picture in Iceland of a town being swallowed by a volcano, that's where this is. So after the volcano swallowed the town and they cleaned up, there's still a town there. And so this is in Vestmannaeyjar. And in the Fab Lab today, it's not yet the molecular nanoassembler, but it kind of lets you do what you would do if you had that. Meaning, there's tools for computer design, there's 3D printing tools and 3D scanning tools, there's precision machining tools to make things like circuit boards and molds for casting, cutting tools to make printing masks, flexible circuits, precision laser cutting for things like the assembly structures, large format for things like furniture composite tooling, electronics rework, and then a broadband video network, so people there are connected to these sites all around the world in a continuous video conference. And so with those tools, here are some examples of what you can do. These are kids in Barcelona making custom skateboards. This was a nice kayak, custom bicycle, all the way up to making a solar house, including the furniture, using those kinds of machines. Instrumentation for healthcare. This is an internet terminal, high gain antennas and networks. This was in Afghanistan. A robotic chess set, a boombox, tooling. This was parts for climbing and tooling to do production. Those are all things you can make once you have that room full of equipment. The research is to smush all the machines together. And to do this, there's consumables you need, like high-tech parts, but once you have all the machines, that's the kind of stuff you can make with it. So these then started spreading virally. And Sherry will tell you about this spread where they've been doubling roughly every year and a half, and there's a few hundred of them. It led to things like, this is President Obama visiting one. This is half of the physics caucus in Congress. This is Congressman Bill Foster, and he's a real maker. And he was so struck by this. This is legislation that's in the House, and it's about to be introduced in the Senate, to set up one of these fab labs in every congressional district as a new take on national infrastructure. The idea is that you provide electricity and sewage in a town, now you provide tools for fabrication. Or another way to think about it is, instead of a national lab being $1 billion remote facility, it's a national lab made out of linked local labs. One of these labs isn't a critical mass, but the network of them is. And so it looks very promising for this legislation. And so once a day, we get contacted by people who want to set up a fab lab. About once a week, we get the harder ones of somebody saying, I'm canceling my life, I'm reporting, where do I go? It's about once a week we get these, where do I go? And so that's gotten way too big as a mutant outreach project. So from MIT, we're still very much involved in the research roadmap, but then we've had to spin off a foundation for operational capacity and an educational program to keep up with the educational capacity. Because what we hadn't really thought through, like the birth of the internet, is if anybody can make anything anywhere, then the vertical separation of industry, aid, education, sort of this cuts across all of those. In one of these community facilities, you can do all of those functions. You can create jobs and play and do art and make infrastructure, but it breaks all of the existing infrastructure, institutional boundaries. And so the hardest part of this project is we found we have to invent new institutions to keep up with the technology. So this book tells that story, and this is a more recent Foreign Affairs article that updates on it. And with that, then, I'll hand off to Sherry to talk about the growth of the network and then the educational growth.